Okay, this is the second lecture on discrete distributions. Talk about discrete distribution, especially the binomial distribution. So one of these special distributions is called the binomial, and we're going to know when it arises in real life. And we look at these properties. First, if you have an underlying experiment which has n independent and identical trials, like tossing a coin, even if it's not fair, it would be a trial, and if you have tossed it n times, each trial has one of two possible outcomes, a success or a failure. So that would be typical for a coin. The probability of success in a single trial is equal to p. It's a constant and doesn't change from trial to trial. And the experimental is interested in counting how many successes are there. Okay. So let's look at other examples that would satisfy this. Say if you throw a die and you're interested only in 6, your success is 6, everything else would be a failure. And that the probability is 1 over 6 of success, and doesn't change if you keep throwing that die over and over. Another example is, say, a few testing items at the assembly line, and you wonder about items being defective or non-defective, and if the machine you are using is known to have 1/10 of 1% of defective items, so that's the probability of a success when you detect a defective item, and doesn't change until something happens to the machine. So that would give you also a binomial experiment. So in that case, x would be the number of successes, and n is the number of times you want to repeat the experiment. P is the probability of success. So there's a formula for that. The probability of having x successes in n experiments, so that's the binomial term. Remember, we talked about this before. P raised to power x, q raised to power n minus x, and x takes values from 0 all the way to n. Q is 1 minus p. It's easier to work with q, but you can put 1 or minus p all the time. And for this distribution, of course, we know how to compute the mean for discrete distributions. Instead of calculating each time p of x multiplied by x and add them up, for the binomial, if you were to do that and simplify, you'll get the mean always equal n times p. Same thing for the variance. It would be np times q, and the standard deviation, the square root of that. One special distribution I'd like to mention always is the Bernoulli, because the Bernoulli is a celebration of the Bernoulli brothers, who started this whole thing about binomial probabilities, and they used it in gambling in the, I think, the 17th or 18th century. So a random variable is a Bernoulli if it's a binomial with where the experiment is repeated only one time, so n is 1. So you can only have a success or failure, because that's going to be px 1 minus p, or q 1 minus x. And it's nice to put it in a tabulated form. X can only take two values, 0 or 1. 1 is the success with probability p, and 0 is the failure with probability 1 minus p. So it's a nice experiment. Mu equal np, so in this case it would be p, the n is 1, here again it would be pq and square root of pq. Before we talk about how to use binomial tables, let me go and give you an example on how do you compute probabilities using the formula. And just look at this example here. Look at, bring up this thing, my tablet, and what's going on here? So let's start with this example here, and the example is, suppose, so I have x is my random variable, and it is a binomial. I use binomial like this one, and with parameters n and p. This is a good notation for the binomial, where I want to use n equal to 3 and p is 0.6. So I'm going to repeat this experiment 3 times, where the probability of success is 0.6. So you can think of it as tossing a biased coin, fake coin, 3 times, where the probability of falling heads is 0.6. And I want to compute the probability that x is equal to 2, say. Okay, so we know from the, let's put the formula here so we can compare. So p of x is equal to what? Nx px q n minus x. So here we would have, just substitute, n is 3, x is 2, I want 2 successes, and p is 0.4, I raise that to power x, which is 2 squared, and q is 1 minus x, so that's 0.6, and that's 3 minus 2. So now we want to simplify, and if you keep these equal signs nicely written this way, you'll never go wrong. So we know this term is 3 factorial over 2 factorial, and 3 minus 2, 1 factorial. 0.4 square is 0.16, and 0.6 raised to power 2 is times 0.6. So let's simplify this term. What would that be equal to? 3 factorial, let's do it on the side here. 3 factorial is 3 times 2 factorial, which will cancel with the 2 factorial here, and then the 1 factorial is 1, so I have 3. So that's 3 times 0.16 times 0.6, and that's equal to 0.288. Okay, so that's how you compute the probability. You can do the probability of x equals 0, 1, 2, and 3, and you can do them all the same way. And you should probably practice with that, with this exercise. Okay, let's check how do we use tables for this. Okay, this is a binomial table which summarizes the probabilities in a tabulated form. This is a portion of it, and it's from your textbook, from when n equal 10, and but you have the table usually for all possible values of n. So the way you read this, and what you have here are cumulative probabilities. So if I have p equal 0.4, this is the one I'm going to use, or let's look at this highlighted number first. This represents the probability I have 2 successes when I toss 10 coins, and the probability of having heads is, or a success is, 10%. Okay. And so on. So if in the example I'm going to give you here, is this: suppose you have a binomial experiment, n equal 10 and p equal 0.4, then what's the probability x is less or equal to 4? So remember, less or equal means probability of x being 0, 1, 2, 3, or 4. And in this case, I would just go to the table and read that. So I go to the table. I need n to be 10. I need p to be 0.4. So this is my distribution here, and you can see from 0 all the way to 9 and 10 would be 1, so that's why it's not given. So if I want the probability of x less or equal to 4, I will just go to 4 here and go make a horizontal line until I meet the point 4, which is 0.633, and that's what I have here. So what if I want the probability of x strictly less than 6? Well, the table gives me less or equal since it's cumulative, so I need to change that to x less or equal to 5, and then I go to the table again. So I go to the table, and now I go to the table which is less or equal to 5, my n10 still. This is my distribution, and less or equal to 5 would be 0.834. Let's see, 0.834, which is correct. So if I want the probability of x greater than 4, well, the table gives me probabilities of this type, less or equal, so I have to convert that. So I want 1 minus, this would be 1 minus p of x less or equal to 4. So this is the cumulative, the complement of this event. But we already did this, which is 0.633. So we get 1 minus 0.633, and I'm done. You just have to compute that. What if I want the probability of x exactly 5? Again, that will be the probability of x less or equal to 5 minus the probability less or equal to 4. Because then everything up to 5, everything up to 4, the difference would be the only thing left, which is exactly x equal 5, and I already did those both. So if I didn't, I would have to go to the table to get this, and go to the table to get this one, which are those two values, and then I get 0.2. So now you have answered the same question with p equal 0.7. And in this case, you would have to go and go to 0.7. So still my n equal 10, but now this would be my distribution. And the first question, p of x less or equal to 4, would be this number here, 0.07. P of x less than 6, or less, which we make it less or equal to 5 to use the table, would be 0.150. Okay, and the last two questions are similar. So do that and make sure you can get it correctly. And that's how the tables are constructed. Of course, there are other tables that are not cumulative. So if you use a different book or different table, you may have just probabilities of x equal instead of x less or equal, as in this case. So you have to be careful when you use the table to use the correct table, or to extract the correct information from the table you have. And thank you.